So now we're going on to conservation of mechanical energy. Um, and conservation of mechanical energy says if um, okay, the only forces that do work on an object, okay, that word has a definition. We need to talk about what that is. But if the only forces that do work on a chosen object are conservative forces, we have to define that, then um, the potential energy of the object plus the kinetic energy of the object is a constant. Okay, so PE is what I'm going to call, how I'm going to label potential energy. KE is what I'm going to call kinetic energy. And in order to do this stuff, we have to know what work is. We have to know what the definition of conservative forces is. And we have to know what potential and kinetic energy are. So the setup for this is defining those four things. Um, so I'm going to start by talking about work. And work is the meaning of it in physics is a change in energy that's caused by the application of a force. Okay, so there are a lot of ways to change something's energy. Energy shows itself in a lot of different forms. Like, for example, if you raise the temperature of something, its energy is going up. But normally, the easiest way, in the easiest cases to think about, if you're going to raise the temperature of something, you're going to do it by putting something with a higher temperature next to it and letting energy flow from one thing to the other thing. Okay. That is not work. Even though that's changing the energy of the chosen object, it's not doing it through the application of a force. It's doing it through the application of a temperature difference. So that's something else. So we're only talking about changes in energy that are produced by applying forces to things. Okay. So, like right now, I'll explain this a little more as we go, but when I lift this up, I'm increasing its energy. Okay. Um, and I'm doing it by applying a force to it. So I'm doing work on this thing when I lift it up. Or also, if I smash it against the wall, um, I'm increasing its energy by making it go faster. by applying a force to it. So the work um, the work that's applied to an object um, between instant 1 and instant 2 is, the work will be capital W, and that's equal to the force that's applied to the object, dot product with the displacement of the object between instant 1 and instant 2. And the meaning of the dot product is you take the x components and multiply them together, and you add that to the y components multiplied together. Um, where f vector is, so that's force vector applied to the object. And d is the displacement vector of the object between instant 1 and instant 2. We're not going to do these calculations, but the intuitive result, the thing that you should keep in mind about this, is that if the force vector is within 90 degrees of the object's path, then W is greater than 0. Call that number 1. If the force vector is more than 90 degrees from the object's path, then the work is less than 0. And if the force vector is exactly 90 degrees from the object's path, W is equal to 0. And what these mean, if W is greater than 0, that means that this force is increasing the energy in the object. So the object's energy increases. If work is less than 0, that's taking energy away from the object, so the object's energy decreases. And if work is equal to 0, the object's energy stays constant, it doesn't change. Okay, so that's all you have to know about work. Let's talk about units here. So this is units of work and any other kind of energy. You know, work has to do with, it's a change in energy, so it has the same units as energy. So work and all other forms of energy. We know from the definition of work, like if you look at how you calculate it here, you have units of force times units of length. And so you can think of that as units of force times units of length, or you can break up force into units of mass times units of length. And now we have those squared divided by time squared. The SI units, that would be a Newton times a meter, which is equivalent to kilogram meters squared per second squared. And because we use this so often, we give it its own name, the joule, capital J. Okay, so the next thing we have to define, that is all we need to know about work. But now let's talk about kinetic energy. We're just going to go through, define all of these 4 things. So kinetic energy. So let m, lowercase m, be the object's mass. And capital V, let that be the object's speed. Then the kinetic energy of the object is 1/2 times the mass times the speed squared. If you, instead of having the object's speed, you know, normally up until now, it's a lot more common that we're dealing with velocity components than with speed. So if the object, instead of being given the speed, you're given the velocity vector. So let's say the object's velocity vector is vector v. and you can calculate the kinetic energy as 1/2 times the mass times the x component squared of the velocity plus the y component squared. So just depending on what you have, those are the two ways you can calculate it. So one thing to notice, well, two things to notice. The first one is as something goes faster, it has more kinetic energy. So as the speed increases, the object has more kinetic energy. And then this is sort of a surprising one, and it's sort of important for an intuitive understanding of energy. That is kinetic energy and this is like every other form of energy, like all forms of energy, is a scalar, not a vector. So energy doesn't have any direction. You know, when you talk about a force, you apply a force of 50 newtons in that direction or whatever. But there's no such thing as an object having energy in this direction or energy in that direction. It's just something it has, like mass. Okay. So energy is directionless. And really, that gets at one of the reasons that doing energy calculations is nice in a lot of cases. You can get information without worrying about what's happening in all these different directions. A lot of times the math is simpler because you're throwing away all this directional information. And if you're looking for the right kinds of things, you can still calculate, you know, what you're looking for. Okay, let's start to talk about conservative versus non-conservative forces. Okay. So a force is conservative if knowing an object's location is enough information to know the force applied to it. We're only going to deal with two types of conservative forces. So for us, that's just first, the weight force, the force applied by gravity. And second, the force applied to objects by springs. That seems like sort of a funny, like oddly specific thing to be worried about. It turns out that spring forces are important in engineering and physics because a lot of things can be represented as springs, but that's what it is. So weight and the forces applied by springs. Everything else is a non-conservative force. Okay, so let me go through